Thank you. And thank you so much for inviting me. As I mentioned a couple of times before, this is my first in-person seminar since 2019. So let's hope this goes well. So yeah, I will be talking about black tsunamis and naked singularities in AdS. But for starters, let me just make a small observation. And the observation is that one of the many reasons why we think gravity should be quantized is simply due to the existence of singularities. These singularities are, of course, some sort of quantum gravity regime that is very difficult to probe in practice. And this is something that's very well embodied in the cosmic censorship conjecture. So the cosmic censorship conjecture basically tells us that quantum gravity regimes which are not covered by a horizon, that is to say, naked singularities, cannot be observed. And they cannot be observed neither by an infalling observer nor by an asymptotic observer. Okay, so this seems pretty robust, and it is broadly valid, this conjecture, except for a certain set of classes. And, well, cases. And these certain set of cases can be generically put into three categories, three distinct categories. So the three categories are the endpoint of black hole evaporation, critical collapse, and Gregory-Laflamme instability. So the endpoint of black hole evaporation, what it basically just tells us is that as the black hole evaporates, eventually it reaches a Planckian size. So it's going to be a very small black hole, and at that point we have no idea what's going on. Semi-classical gravity breaks down. It's a singularity. Critical collapse refers to the collapse of a star. So we have a star collapsing and forming a black hole. However, we can play with the parameters of the star such that we can fine-tune them and make just a small Planckian black hole. So in that sense, we reach the same conclusion as for black hole evaporation, that we have a naked singularity. And Gregory-Laflamme instability is something that I will be talking about mostly in this talk. But just to give you an idea of what is it about, it's about basically horizon ripping off, tearing apart, and at the places where the horizons tear apart, this is where we get the naked singularities from. Okay, so we see that we have three distinct violations of the cosmic censorship conjecture. However, all of them have something in common. And that something is that they're all very small in a very particular sense. So what I mean by that is that they have a Planckian extent, they have they last for a presumably very short amount of time, Planckian energies. And maybe one can make a modified cosmic censorship conjecture by saying that, well, I cannot observe large violations of cosmic censorship, but these small types of violations can be then allowed. Okay, so it seems like with these small naked singularities, we could actually try to probe this quantum gravity regime. But it's a little bit difficult to think about how we would actually do such a thing. Luckily, there is one way to look for what sort of a signal these sort of singularities would give us, and that is to simply look for their imprint on the boundary theory. And this is something that has been already done in the case of the critical collapse by Chesler and Way a couple of years ago. And in this talk, we're going to focus on the same type of singular signals that would come from the Gregory-Laflamme instability in AdS. Okay, so I will cover first some basics of Gregory-Laflamme instability. We will then see what kind of tools we need in order to evolve these black strings that the Gregory-Laflamme refers to inside AdS. I will present what sort of evolution scenarios we can get out of these equations that we employ for the dynamical evolution of the black string. And finally, we will see how to obtain the boundary signal that I just talked about. Yes?
You were saying somebody did something like that, critical collapse scenario?
Yes.
Is what you're going to do going to be related to that approach, or just like a totally different story that has nothing to do with that?
Actually, we will get to some point in the talk where I'm going to review their calculation. That was not in the paper. Their paper was mostly about the numerical part of it, which is the nonlinear evolution. but they have a linear argument, which is purely analytical, and I'm going to present that argument here. So
they also use a large view approximation?
No. That was, well, you will see, but for the extraction of the signal, we will also not use the large D approximation. The large D approximation is only used when we want to evolve these black strings, perturb them in some way, and see what kind of configurations we get. But for the actual extraction of the signal, we use a toy model. You will see there was, I don't know, slide number 17 for sure. Any questions? Other questions? Okay. So recall that the Gregory-Laflamme instability in flat spacetime, at least the way that Gregory and Laflamme first introduced it, revolves around a black string, which in their case was in 5 dimensions, but it doesn't really matter what number of dimensions it is. And a black string in 5 dimensions is basically a Schwarzschild 4 black hole put on every point on a circle, so to say. So this is some sort of an extended object, and as an extended object, we can compute its mass and entropy, but we can also ask the question if this extended nature of the object is the preferred state. That is to say, we can ask if it's thermodynamically preferred with respect to some other competitors that one would have in a thermodynamic ensemble. So in order to see if it's preferred, we have to see what its competitor is going to give us for the mass and the entropy. And its competitor is basically going to be a 5-dimensional localized spherical Schwarzschild black hole. So we compute these quantities, and we compare them. And once we do that, we see that there is a regime of some parameters for which there exists a phase transition. That is to say, if we have a thin enough string, we start with a string which is thin enough, then the preferred configuration is going to be actually the spherical black hole. That is to say that this thin string that we started with is going to be unstable to perturbations. It's going to have to want to evolve into something else, and that something else is the spherical black hole. So this thermodynamic argument can be verified by a linear analysis, actually seeing that this start of the perturbation is actually leading to some sort of a different configuration. And this is what Gregory and Laflamme did in 1993. But one could also do a full nonlinear analysis, of course, through tedious numerical work. And this is the seminal work of Lehner and Pretorius from a little bit more than 10 years ago now. So what Lehner and Pretorius gave us is this nice little snapshot here, where we see that we start with the black string here at t equals 0. And as time moves on, this string starts to wobble in a sense. It starts forming these little spherical black holes, eventually reaching this sort of a configuration where we have spherical black holes connected with thin tubes that have horizons, that are basically covered by a horizon. And the pinching of the horizon of this thin tube is actually where we get the naked singularity from. So our string starts to wobble, it starts to stretch out, and where the tube gets very thin, this is where it tears apart, this is where we get the naked singularity from. Okay. So what are the relevant parameters for this instability? So we saw that we saw that we have to compare the length of the string to its thickness. So we said that the string needs to be thin enough in order to give us this phase transition. And the thickness compared to the length of the string is what gives us some sort of a dimensional ratio that we can then look at and deduce whether or not there's going to be a phase transition. So that's for flat space. If we try to put the system in a box, that is to say AdS, then we simply replace the length of the string with the AdS radius. And so basically we replace the length of the string with the size of the box. And so we have to see the size of the box compared to the size of the string. And that's going to be our dimensionless parameter that's going to tell us about phase transitions. Yes?
In the flat space case, you were saying the solution is just Schwarzschild, let's say 4-dimensional Schwarzschild crossing S1, right?
Mm-hmm.
Is the solution now 4-dimensional, let's say 4-dimensional Schwarzschild AdS crossing S1? Or?
So that's this slide. Is this helping? So this is basically the metric for the black string that you have in AdS. Or specifically, you have some fixed geometry on the boundary. And on the boundary, this looks like you just have some two black holes at the equator.
Yeah, but that's like a warped product of the lower dimensional shots of AdS with another.
Yes. Well, I mean, at each constant z slice here, you have a black hole.
Yeah.
And so you have an extended horizon that goes all the way from here to here. And so in that sense, it forms a black string.
What would have been wrong with considering the direct analog of the black string? In other words, are there solutions that look like shots of AdS plus a circle?
I'm not sure really what you mean. Why isn't this the direct analog? It's the most natural one. You put the black hole on each constant slice.
It's just a Kaluza-like complexification, right? I can think of it that way, right? It's just some known solution cross a circle, direct product. So it would
For the flat case, yeah.
Would seem like that's
yeah.
That's a very easy thing to generalize, and the generalization, I mean, to AdS will not be this. I mean, obviously, if you study whatever you like, I'm just trying to understand.
We can probably consider unstable but quasi-stable thing that the thickness is bigger than AdS radius, and then it just has S1 if you want to think about it. That's just simply geometrically not as simple as this, and then probably unstable in a longer time scale.
Yeah. I mean, I think you can study, as you mentioned, you can study various these black objects that have extended nature. The nice thing about this one is that it's in AdS, so you can literally like compute its boundary dual, for example, if you wanted to, which is one of the reasons why we want to do this here.
So probably if the thickness is already much bigger than AdS radius, then even if what you do like S1 or whatever, it's stable.
It's going to be stable, that's correct, yes.
And some other thing will happen, probably gravitational wave and so on.
That's the correct intuition, yeah. And for thick enough strings, it doesn't matter how hard I punch it, so to say. It's not going to budge, it's going to be stable. It's really when you go down below some particular scale that you're going to see all of these instabilities. But particularly here, yeah, I would say that the reasoning is that we want to study also its boundary dual, and so you would want to have this sort of a setup.
Sorry, just to understand Raphael's question. So before, in the work, that was before the string was a circle.
Yeah, you can put a black hole on each point on a circle, so to say. It looks kind of like a black torus, if you will.
Right.
And then that torus can wiggle around. You can also take the limit where it's literally flat, but then you have to be a little bit careful because now you have infinite length. But it leads to the same type of a conclusion.
Right, so in here it's not going to be that, it's going to be a string that really is attached to boundaries.
Yeah. That's going to be important because there are these black holes that are on the boundary. And the boundary is a fixed geometry. So that's also important to keep in mind.
Do these strings have some weird source in the boundary? Or like, does it have crazy behavior, or is that like okay?
Do they have a crazy what?
Behavior? Like
behavior.
That
Depends on what you mean by crazy. They don't have anything.
For instance, just doing like Pfefferman gradient expansion and things like that.
Yeah.
In this case?
Yeah, so for this particular state, which is just a uniform string, it turns out that you have zero stress tensor on the boundary.
Oh.
It's a very particular, peculiar state. Some people have calculated it. I can give you a reference.
Okay.
Yeah, but the moment you start perturbing it, of course, there's a non-trivial stress tensor forming on the boundary. And that's exactly what we're going to look at as we look at different configurations in the bulk. So you're going to see different black objects wobbling around in the bulk, and all of those are going to correspond to different configurations of Hawking radiation on the boundary, so to say. Yeah, but that's all upcoming. Yeah. Any more questions? Good. So this is a metric, and with this metric in particular, Hirayama and Kang already showed us that with their linear analysis, that a thin enough string is going to want to pinch off. So this is what we already kind of knew, but they were the actual ones to perform this linear analysis, which is kind of analog to what Gregory and Flamm did in '93. So what they saw were these initial bumps, so to say, initial wobbles. They saw the indication that it wants to pinch off. Of course, what we're going to do now is go beyond the linear perturbations, so to do the analog of Lanner and Pretorius. And, well, doing the full numerical analysis is something that some our collaborators are currently investigating, but it's requiring a lot of power. So what we're going to do instead is employ something called the large D effective theory in order to make our life simple to evolve these equations in a much nicer way. So what is this large D effective theory then? So large D approximation was introduced by Emparan and his collaborators some years ago now. And it was basically introduced as a way of effectively separating scales. So they wanted to analyze the dynamics of the horizon. And so what they did was basically put a lot of space-time dimensions, so a large number of these dimensions. And this large number of dimensions would then suppress the effect of the gravitational potential away from the black hole, thereby effectively separating all the black hole dynamics from the rest of the space-time. So the rest of the space-time is just flat, and then we have big gravitational potential next to the black hole itself. Okay? And one can do this rigorously. And so with this suppression, of course, we get an amazing simplification of equations. And because we have simplified equations, we can perform much more complicated evolution scenarios than we would have with just the usual GR in the finite number of dimensions. And this is something for numerical people here, this is something one can do in seconds, minutes, something very small. Okay, so how can we apply this approximation in this setup then? Well, we start with the black string in AdS, as we did before. So remember how the metric looked before? But now we're going to write it in a slightly more convenient way. And so you're not going to believe me when I show you this and I say this is more convenient. But it is convenient for employing the large D approximation. So this is the same metric as I showed you before with some various sort of coordinate transformations. What's nice about this form in particular is that now we can define these variables that we can keep fixed for when the number of dimensions goes to infinity. Okay? So x and r, the big R, these two things, are going to be fixed when n goes to infinity. And what this basically does for us is localize the geometry near the center of AdS. So this is what x coordinate does for us. So z goes to 0 is the center of AdS, n goes to infinity. This is low. This is finite. But it also localizes us near the actual horizon. So we see that in this r coordinate, r has to go to r0 if we want this to keep fixed. So why do we want to go to the center of AdS and near the horizon? Well, that's because that's where the string is the thinnest. And so when we have a thinnest string, of course, when we perturb it, this is the first place where the pinch-off is going to occur then. Okay? So we want to actually focus on this region where the pinch-off is occurring. So this very convenient form of the metric then inspires a very convenient form of the ansatz for the perturbations. And the details here are really not important. What is important here is that we get some functions m and p. And these functions themselves can give us the equations. Sorry, we can obtain the equations for these functions from solving the full set of Einstein's equations. So these are nonlinear equations. They're not small perturbations. And what they give for us is simply a very sensible set of equations that we need to solve. And what these equations actually provide us with is an effective theory of dynamics of horizons in AdS. Okay? So that's all that you need to know about large D approximation, at least for the purpose of this talk. Okay, so we have these equations. They look simple enough to solve. One can solve them, evolve them. And by solving them, we can obtain many different configurations for the black string in AdS. But even before we do that, we can intuitively already see some possible configurations that we can have. Okay? So for example, we can have droplets, which is basically just two separate black holes in the boundary. We can have bulgy, fat funnels, so to say, which is an analog of large AdS black hole, just connected with these tubes to the boundary. We can, for example, have droplets with a black hole in the middle. This is yet another configuration that we can have, and so on and so on. Of course, to see what are the relevant phases, not just a list of all of them, we have to perform the thermodynamic analysis. And in order to do that, we're going to evaluate our phases in the canonical ensemble. So why canonical ensemble? Well, it's basically because we have our boundary black holes acting like heat sinks. Simply, they are allowed to exchange the energy with the CFT, and therefore CFT degrees of freedom are allowed to flow inside the black hole and leak out into the bulk. A more geometric way of saying this sentence is to see that horizon generators can basically flow in and out of the boundary and into the bulk. And this inflow of horizon generators we have named black tsunami, which at this point in the talk doesn't really make any sense, but I promise it's going to make sense. Let me just note that also in these cases, there is something called the free energy theorem. And this is basically the canonical ensemble analog of what we would have instead of an area theorem. And it basically tells us that our free energy has to go down if we apply some physical processes. And of course, states with the lowest free energy are going to be the preferred ones. Okay, so the thermodynamic analysis actually was already performed by Don and George a couple of years ago, among other things that they did in this paper. And what they obtained is the following. So they saw that these uniform funnels, these simple black strings, can dominate when they are very thick. This is exactly what you said. If they are very thick, doesn't matter how I perturb it, they're going to be stable. And this is analogous to the flat Gregory-Laflamme case, where we have simply a flat, when we have thick flat string, also not budging down to our perturbations. However, the things get interesting when we have a thin enough string, so for thin enough funnels. You would expect that maybe you would get droplets to be the dominant solution now. But instead, what they obtain is that fat funnels are the dominant solutions instead. And this is very much unlike the flat Gregory-Laflamme case for which the droplets would be kind of the analog of these spherical black holes that we expected. So this is a little bit strange because such a result would then naively indicate that maybe we are not going to get any naked singularities in the bulk, given that we just simply have to go from this very well-connected object to this even more connected object here. And there's no obvious route where this would lead to some sort of a pinch-off in the middle in the evolution, right? Yes?
What do you mean that for thin funnels, fat funnels dominate?
In the thermodynamic ensemble? So, right. So they just compared, they did the thermodynamic analysis, and they saw that for various parameters, for example, this size of the string, what would be the dominant solution is not what you would expect, that is to be the droplets, just the two black holes, because their entropies, their free energy is not low enough, so to say. The lower free energy is going to be actually coming from this fat funnel phase.
So thin funnels fat?
Yeah.
Okay.
It's a little bit counterintuitive.
Thin funnels.
Yeah, yeah, that's what they found to be the dominant configuration, yeah.
So what's the thin and the thick? Is that the size of the boundary black hole compared with the radius at the cutoff?
You mean the dimensionless parameter that they use?
Thin and thick.
Yeah, so it's basically what we were saying before. It's the size of the AdS curvature, basically, compared to the size of the string where it's smallest. So to say in the...
where it's the smallest. Yeah, that was a question.
Yeah, exactly, yeah.
But what will change is probably boundary black hole size, right?
Um,
Responding to that, probably the center changes as well. But
well, I mean, I think you can change both. But what you physically want to change is, I think, the middle of the string. So you want to make it thinner and thinner.
what's the parameter in boundary theory to do that if you fix the size of black hole?
It's the size of the black hole in the boundary.
Oh yeah, so you're
Yeah,
changing
yeah.
that, right?
Yeah. Sorry, yes, of course. Okay, so I mentioned that it looks like there couldn't be any sort of naked singularity forming, but of course, that cannot be true, because we know that as we zoom into the AdS center, what we're going to see is just this black string, not seeing the AdS asymptotics. And so it's basically going to behave just like a regular old flat, regular Laflamme unstable string. That is to say, it's going to behave nakedly singular. Nakedly singular. Sorry, yes?
This is related to the previous question, but when you say that for the thin funnels that are also non-dominating set fat funnels are dominant, is that just analogous to, if I start with a small black hole in AdS, and I put the boundary at the temperature corresponding to that, then instead it's going to make a big black hole because that's the stable configuration?
For sure, this fat funnel is an analog of large AdS black hole. I mean, the analog is simply that you look at, you have to look at an extended object here. I mean, I think you can look at it also these metastable objects like small black holes, but I can't give you an exact result there.
I mean, I'm trying to understand whether the ensemble that you're putting this in can be thought of intuitively as a thermal ensemble for each Z. In that case, you would expect this kind of thing to happen, right? And you would expect the thin black hole at each Z to become a fat one.
I wouldn't say this was expected. At least for me, this was a little bit surprising. Yeah. But I mean, the thing that you're doing is basically, you have this one parameter, right? Which is dimensionless. So it's the ratio of the size of the string, basically here in the middle of the AdS, or basically the boundary black holes, compared to the size of the box. And so you simply expect that, if you make your box large enough, for example, and you keep your string thin enough, this should effectively be like a flat case. And so I would have expected immediately there to have just droplets. The fact that we have these funnels, the fact that we have funnels forming, though, I think is more of the construct of us having this fixed boundary conditions, fixed boundary geometry, and therefore you're allowing this infinite inflow of these horizon generators. They can.
Can you think more about the boundary conditions, like something analogous to, I can put the CFT in a thermal state, by basically just taking a Euclidean configuration with, the boundary sphere across an S1. And then I can do a path integral that asks what are the dominant configurations, and depending on the size of the S1 compared to the boundary sphere, it's either going to be a black hole or not. And is there something analogous that I can think of here that lets you construct these that constructs your ensemble in which you're operating? I'm having a little bit trouble understanding what the boundary conditions are.
The boundary, you just have a fixed geometry on the boundary. It's infinite n, fixed geometry. You just put a black hole there.
If it's a fixed geometry, I can ask about what dominates, right?
Yes, and that's what we're doing here.
But I don't understand that. So if the geometry is fixed, then I can ask about it. I cannot ask about any other geometry. Like in the thermal ensemble in AdS, I can ask, what's the dominant configuration? A gas of photons or a black hole? Because I'm putting boundary conditions that in principle allow for both, and then one is going to dominate over the other.
I think the way you should think about it is that on the boundary you have black holes that are fixed there. They're just there, they don't back react, so to say. And then you have different states of your CFT stress tensor, of the Hawking radiation. They can pour in or out or whatever you want to do with it. It's basically doing QFT on a curved spacetime on the boundary. Your energy is not conserved on the boundary. It can flow inside the bulk. That's why we have the canonical ensemble. Because the energy can flow from the boundary to the bulk. This is why we get dissolution that we have.
Never happens. I mean, the boundary is, you can think about the boundary as a CFT, presumably that doesn't, it doesn't require a bulk interpretation. You can discuss it, right? I thought it was interesting.
So the way that you should think about the boundary, at least the way I think about it, is just fixed geometry with any stress tensor that I can put on. Just Borel-Davis quantum field theory and curved spacetime type of a thing.
But then then the energy has to be conserved.
What I meant by this is simply that this CFT that's on the boundary, the quantum fields that are there, can flow inside the black hole.
So
right?
Your boundary theory, not the boundary of the bulk theory, your boundary theory is simply just not static. Is that right? Because otherwise it's just a boundary theory. You just start the static, the energy conserved in boundary theory, not the boundary of the bulk theory. You do the holography, you go to CFT. And anything going to bulk is also some states of the boundary theory. If you just go
Yeah, like changes in the bulk correspond to changes in the stress tensor of the CFT on the boundary. That's how you should see it.
So just
changing the
bulk
bulk
theory is time dependent, right?
Do you have
in
sources
that
the boundary
sense.
that correspond to sending matter? I mean, what is the analog of this in ordinary CFT where the boundary is just a sphere across time? That CFT has to have energy conserved unless you change the Hamiltonian, you add sources or something, and then both the bulk and the boundary can have changing energy.
In a vacuum. So C probably puts some energy momentum tensor or something which like
Yeah, like the Einstein equation, are you solving it in the vacuum or do you have a source there?
so it's not
So-
a static system.
So we're solving just the Einstein's equations in the bulk,
Yes, yeah, but
Yeah, that's fine. But
which can be
corresponding
perturbed, and those perturbations, of course, correspond to some sort of a stress
source.
tensor.
So like
Yes.
we're sourcing something then in the boundary.
Yeah,
right?
exactly. That's what I meant by different configurations here in the bulk correspond to different CFT radiation on the boundary.
So what sort of sources do you couple to the boundary? What are you sending in?
So from the bulk point of view, you have a purely classical bulk, where you have some sort of a metric, and you have perturbations on top of this metric. So these perturbations correspond to your stress tensor, if you will, on the right-hand side of Einstein's equations. And you can read that off also on the boundary theory as a different stress tensor corresponding to different perturbations.
So it's
Just Pfefferman and Graham.
simply not static, but fixing temperature means that you're thinking some path, right?
Yeah.
So you're always keeping temperature, not keeping energy. It's not
Yeah,
like
that's the
you're-
canonical
I
ensemble.
don't understand that. In the canonical ensemble, ordinarily in ACFT, energy is conserved.
Oh, if it's a static. But if you just do something and they keep the temperature, then it's...
So the energy is always conserved, but the dynamic, the stress tensor is locally conserved. And the total energy of the CFT is also conserved, whether there is interesting dynamics or not. The only way to not have that happen is if you change the Hamiltonian.
Well, if this air of this room is in thermal contact and a thermal equilibrium with something else, and if you change, then you can have energy exchange with the environment.
So maybe I can postpone this question to after the talk where I can show you what I mean exactly by showing you this free energy theorem.
The energy the expectation of the energy, which is all you know how to calculate.
Yeah, if it's a thermalized.
So-
that's why it shouldn't be.
Whereas here, it sounds like the expectationally the energy is changing in various places. At least that's how I interpret
Oh,
it.
expectation
That
of
same
something.
thing is being sent in on the boundary.
There's nothing unphysical going on, but I think maybe we
Okay.
can postpone this question where I can actually show you what I mean by it through equations. Is that better? Simply because I can move on and show other things. But I will show you in detail the free energy theorem, and then we can go through it.
Can I ask one more question? Just because this whole foliation is very reminiscent of a quadrangle type foliation where you foliate AdS into other AdSs, except that your AdSs have black holes in them,
Mhm.
right? So can I think of the conformal structure of the boundary itself as basically two copies of AdS-Schwarzschild glued to each other across their boundary?
Yeah.
Is that the right picture for the diagram?
Yeah, so the way I understand it is that your boundary theory should basically be some sort of CFT left cross CFT right, but now the CFT left has two black holes on them. And also the CFT right has 2 black holes. So it's like two thermofieldable states.
And they have to be coupled to each other, right? Because
Yeah. Yeah. So this is the right asymptotic region, if you will. This is the left asymptotic region.
Oh, I thought it was really right on that in your picture. On bottom and top.
Well, I mean, this is, yeah, sorry, I didn't understand.
I thought that the picture I was supposed to have is that this is really a warp compactification with each slice being AdS Schwarzschild.
It is each slice,
So
yeah.
The boundary consists of 2 copies of AdS Schwarzschild that are glued together at the top.
Yeah, that's true. Yeah, that's true. Okay, so let me just move on to show you our result. So we have all these different phases that we want to see achieved dynamically. And so what we could do is we go to our large D equations and we spend some minimal amount of time in Mathematica. And what we get is the following. So we start always with the same thing, which is a perturbed string. We perturb it in several different ways. And for example, one outcome of these perturbations is going to be, of course, the direct evolution to the fat funnel. So this is something that was expected. This is what Merolf and Satas told us. So we just obtained this sort of an evolution. Now, how can I have to click here? I can't show you. Oh, no, I do. Okay, nice. Okay, so you saw that. I'm not sure that I know how to.
Let me see. In that picture, the size of the black hole on the boundary stays fixed, whereas in the picture on the left, it looks like it got small.
That's because we are not very good artists.
We didn't right. It must stay fixed, right? Because these are the boundary divisions you're floating.
Yeah, of course. They are fixed, yes. Yeah. Yes. Okay. Is this going to work? Yes. Okay. So that, what you saw right now, was an evolution with the actual equations in Mathematica using this large D approximation. And that's how we get the direct tsunami. But of course, we can get other things as well. And one of them is the thing that we actually came here for, which is the pinch-off. So we actually obtain that in substep of our evolution, we get that this string really does pinch off in the middle of it. And we get some sort of a picture like this one, which I guess if I click here, it does it. Yeah. Okay, so we see that there are these 2 black holes forming, and there's a very thin tube connecting these 2 things. I don't know if it's actually visible, but you can imagine it. And they're going to pinch off at some point. Okay. Of course, this is just an intermediate step. This intermediate step then evolves into some sort of an endpoint. One of these endpoints is then the thing that we were looking for as well, which is this 2 droplets on each side of the boundary. So this is a metastable endpoint, meaning non-perturbative perturbations can kick it out. But that's not the only thing that we obtain. Okay, sorry, I also have to show you this one. So this is only to show that these 2 things really do pinch off. There's a slight difference with the previous one. Okay, but that's not the only thing that we obtain, because we also obtain this fat funnel evolution simply from this pinch-off. And so it's a little bit strange to imagine how this would happen. But of course now we can understand the reasoning behind the title of our paper, that this is some sort of a tsunami. So why is this a tsunami? Well, we see that there is a pinch-off going on, right? So the string starts to pinch off. It starts to have these tails that are receding from it. It's kind of like water receding, exposing the seafloor, before then getting completely engulfed by a massive tsunami that overflows it and just covers up the singularity. So how does this look like in actual equations? That is to say evolution. It looks something like this. Of course, the dynamical evolution is a little bit limited. You can't see the exact engulfing, but you can imagine it getting completely covered by this massive tsunami.
So what changed to get all these different evolution,
different perturbations, yeah. Yeah, exactly. So we just showed that there are many different endpoints. And there are, of course, other more complex solutions, like, for example, droplets that have a little black hole in the middle. That's also something that can happen. But these are the basic ones that we obtain.
If you turn all of your perturbations on a little bit, which one is going to happen?
Probably this one, because this is the only one that's thermodynamically dominant in the end. So everything that you do at the end, meaning all of your metastable solutions, you perturb them hard enough, they're all going to end up in this fat funnel phase. That's simply the thermodynamically preferred one.
But the evolution might first evolve in the shot.
Yeah, the evolution can take you through many different phases. It's just going to give you other unstable midpoints, so to say. Yeah.
How many parameters do you have for the perturbation?
So there is size of the perturbations, or to say the amplitude. There's the sign of the perturbation, so it can go like a minus or a plus, like do we have an importing or like ripping. And then you have just simply this the size of the initial string. That's also something that you have to take into account.
So you must be coupling this explicitly for feedback, right? It's not like you're already starting out in some kind of fixed canonical ensemble. You're letting it find the dominant empiric by explicitly coupling it to some external feedback. These don't have the same energy in them.
I feel that that is correct answer, yes.
So
So this, yeah, sorry, I just want to make a comment that this one has the lowest free energy of all of these solutions. So that's something that you should keep in mind.
So your kind of puzzle is that because it looks like a flat space, you have to pinch off, but on the other hand, thermodynamics things said not the other way around. But the point is, if you wait long enough time, longer than AdS,
Well, it's going to be actually,
you can come in, and then it's really like a sensing AdS.
so I think this pinch off actually occurs on a very short scale. So it's kind of like just, it pinches off and then it immediately gets engulfed.
Oh, is this a tsunami thing? Is shorter than AdS scale, time scale? Then I'd be surprised, because then it's locally have to be flat space.
I mean, locally it is flat space. Yeah.
So then why if some other thing happened must be because time, you waited the time.
Well, yeah,
for
you
the
had to,
AdS,
okay, fair enough, fair enough. You
therefore
had to wait that,
everything could be quite different.
okay,
right?
fair enough, yes.
Yeah.
You had to wait some time.
And also
Yeah, but it's not yeah, okay, sorry. What I wanted to say is that the actual pinch itself
oh, yeah, that's
something that
because
lasts,
that's
yeah.
physics.
Yes,
But then,
exactly.
Why your final thing suggested by thermodynamics and your intuition, why not your, but it's just puzzling intuition is different, it's because of time scale, that you wait the time scale over
Yeah.
than AdS, then
Yeah,
you
yeah,
can prove system can
I mean,
prove.
yeah, exactly. And also this is something that you wouldn't get in flat space. There is no reason for why you should get any sort of importing of this sort in flat space.
And you said metastable, but it need not be necessarily metastable if this is almost negligible in a phase space, because that's still consistent with the thermodynamically big thing is the dominating.
Yeah,
This
I
is
meant
the explanation that-
I meant metastable only in the sense that this is the actual thermodynamically preferred
but
solution.
thermodynamics is just,
But it's,
looking at
but yeah, you can get dynamical endpoints, which are simply giving you dynamical stable endpoints,
yeah,
and this is one of
it's
those
smaller
things.
than
Yeah.
The thermodynamics is not sensitive.
Yeah, that's true.
So for
Okay,
generic
sorry.
perturbation, it goes to direct tsunami. For generic perturbation, it goes to direct tsunami and other some special value.
Yeah, I think so. I think that's correct. I can show you the equations. It's very easy to play with them. I guess that's how we got all of these things. Just putting random things that you can imagine and then obtaining different solutions. For us, it was important to get this one in particular because this is what we want to study. But yeah, you can get different things, but most likely this one. Okay, so of course, this is just a classical picture. I can give you a hint of how this looks like from the dual perspective. From the CFT point of view, these are, as we mentioned before, different phases are just different Hawking radiation scenarios. And so what this basically corresponds to, this perturbed string would be some sort of black holes on the boundary with a halo around it. That's a Hawking radiation halo. The direct tsunami would correspond to flooding of the entire universe with this Hawking radiation, because it's an analog of this large AdS black hole. The pinch-off is some sort of a radiation burst. So this is a very localized thing in the bulk, so this is very dilute on the boundary, and this is what we're going to study more. And of course, metastable points are just, again, some CFT halos, and delayed tsunami is a delayed flood. So this is a picture that we can infer just from these classical bulk pictures. Okay. So, but what I'm interested in most is this scenario over here.
Was this just a quick, is this all you're going to say about this? Stool perspective?
Online, yes.
Because that was like, that seems really interesting, but I didn't understand it at all. Could you just go over that a little more slowly? So,
Okay, so these are just expected. What do we expect this would correspond to on the boundary? So basically here you have these black holes that now have been perturbed. So you have some sort of a delta G, if you will, in the bulk. This corresponds to some sort of a Hawking radiation on the boundary.
well, how is that possible? The boundary doesn't have gravity, right?
No, but it has CFT on it. So
Right.
on the
So
boundary you
if
have,
gravity, how can it have Hawking?
you just have some sort of a stress tensor around your black holes. It's just quantum field. And they're around the black holes, presumably because there's a strong coupling, so it's like a plasma around the black hole. It's not something that would freely flow. That's at least how I understand it. So that's why you have, that's what we call them CFT halos, so to say. And the same thing goes for these guys, because these guys are the same basically as this one. Just a little bit more of a halo, if you will. And then,
What do you mean by radiation burst specifically? All these things happen really fast, right? So they have nothing to do with Hawking radiation in the usual sense.
yeah, I mean, I would say that I think you should think about it in the sense of, okay, no, actually I take that back. So first of all, what you have on the boundary is a CFT that has infinite n. A large n, what it gives you is also a very fast evaporation rate. So that's something that happens because you have many different channels where you can evaporate into. But you also have this strong coupling effect. So the strong coupling effect is basically going to keep your radiation in this halo zone here. Like this is not something that we explored extensively. This is just simply what we infer from our solutions as some sort of a cartoon. What would it be on the boundary?
Is the black hole on the left a large black hole that is extended to AdS? The black hole is line in this particular example.
The boundary is not AdS.
Yeah.
Sorry?
So boundary is not AdS, but
It's Schwarzschild AdS, and I'm asking which Schwarzschild AdS it is. Is
Yeah.
it one with a large black hole?
from boundary
Does that matter?
picture, you don't have AdS then.
I thought the boundary is two copies of Schwarzschild AdS black holes.
No, yeah, it is. It is.
Oh, is it two?
It's a Schwarzschild AdS, and then you have at each Z, you have a Schwarzschild
That's why I was
AdS.
asking if like you can do peppermint wave and things like that. Like usually AdS CFT, right?
Yeah. That's what you do in order to infer the stress tensor. That's true.
Sorry, then I was, probably misunderstood.
I guess it is. It has to be, right? If it's Schwarzschild AdS. But I'm not sure. Don't take my word on it. I'm going to have to think about it. But I would say right now, yes.
I mean, are we supposed to understand, presumably this isn't some sort of intrinsic dynamics of Schwarzschild AdS black holes that would just normally happen? It's something that has to do with coupling the boundary to another system, and that's somehow injected.
The way I imagine it, is basically just, you're just studying, maybe I'm imagining incorrectly, but the way that I was thinking about this usually is that I have a black hole space-time, and then I can put various different CFT quantum fields on top of this space-time, right? So I can just put some sort of, whatever, conformally coupled, massless scalar, whatever you want, and then it can have any sort of a form that you want to have. You put some different stress tensors that would presumably then correspond to different configurations in the bulk.
Now that you were saying like large AdS black holes, when you're approaching a boundary, right? Then it has to be because otherwise it's more than cutoff of the CFT.
Yeah.
So it's just in that sense it's large black hole. Always.
Okay.
If you think about the classical thing at the boundary, then it's always.
Yeah, that's true.
So what they're doing is like you have a stress tensor configuration for the boundary AdS Schwarzschild, and then you perturb some stress tensor to some amount and see the time evolution. That's what you're doing.
So So the stress tensor, yeah, okay. So we're always, what we're doing is always in the bulk. So that's always classical GR that we're doing in the bulk. And then you can try to map it. What does it mean on the boundary, okay? So in the bulk, what we do is just put delta G. It doesn't have to be H mu in the sense small linear perturbations. It can be whatever kind of a perturbation you want. And these delta G's have, of course, some sort of a stress tensor associated to them. And this is the stress tensor that you can also map to the boundary geometry. So that's the sense in which you can think about this. But of course, what we did, as in what is in the paper, is just classical GR evolution equations. All these sentences that I'm saying right now, what this would mean in the dual CFT is what I assume it would mean in the dual CFT, but one would actually have to go calculate, see, and so forth. Okay?
Can I just summarize, like what you did actually in computation is all in the bulk?
Yeah.
And all in classical regime?
Yes, except for the last part, which I haven't got to yet.
But so then it's not like reproducing singularity and CFT computation. So no, you do it in the bulk.
I do
but
everything
then
in the bulk.
interpret this phenomenon, pinching, from CFT language, using
so this
AdS CFT, and then you just guess that what we call this singularity in the bulk must be some phenomenon in CFT or something.
I will get to that right now. So what do we say about the singularity itself? Here, these were just words, but now I'm going to tell you exactly what we actually obtained. Yes.
Yeah, probably some global.
Well, we're going to see. I mean, it's going to be, well, for me, it's going to be interesting, but we're going to see if you think about it as well.
Can you say briefly what these pictures mean in the CFT? Like, what's the difference between a radiation burst and a radiation flood? What's that difference?
This is supposed to indicate some sort of a faint, sort of a small energy density, sort of, like you have a localized excitation in the middle of the bulk. It's going to correspond to something very dilute. Boundary. That's sort of a thing that I would expect. Whereas here, this is, just think about large AdS black holes. So that corresponds to some, flow of CFT on the boundary.
And in both cases, so this was very homogeneous now. The fact that in all of these cases there's still these bubble types setups near the boundary doesn't make the boundary stress tensor inhomogeneous. Or there's no feature in the CFT near these two black spots.
I'm not sure what you mean by that. I mean, this is a cartoon.
I'm interpreting the pictures to mean that after the radiation flood or the delayed flood, the stress tensor is exactly homogeneous on the boundary.
Homogeneous. Oh, okay. Yeah, there's probably going to be something over here that's going to be a little bit different. Again, this is just a cartoon.
Okay.
Or what you should expect to see.
Okay. Yeah. By this figure, radiation burst, you like just axial symmetry only, and you wanted to just show that the non-local, right, by this figure.
Basically. Okay, so let's get to the actual singularity then, because I realize I have 5 minutes. Good. So, no, of course.
Marija, because before I ask a lot of questions, you can go over.
I have 10 minutes, okay. Okay, no, this is very good. Okay, so we obtain a naked singularity in the bulk. As we saw, we can get it through this evolution. But of course, what does this actually look like on the boundary? I gave you some sort of a cartoon. What can we actually say about this signal that we can obtain? Now note that in order to extract, so to say, real physics from this, large D is not going to be very useful in this case for the extraction of the signal from this naked singularity to the boundary. And this is basically because large D is an effective theory that works best when we want to study horizons and very low curvature regions. And a singularity is exactly the opposite of both of those things. It doesn't have a horizon, it's not low curvature. So actually extracting anything about the singularity is possible, and this is something that Ryutako and Roberto have done, or are doing and developing and so forth, but it's something that's kind of tedious and would require non-perturbative corrections in 1/d. And so we decided not to follow that path. What we decided to do instead is to focus on a simplified setup, that is to say a toy model, in order to extract the relevant signal that comes from this naked singularity, okay? So the logic here is now throw away everything regarding large D when we start from scratch, okay? And so what is our setup? There are 3 main elements of our setup. So the first thing, of course, we're going to model it with respect to the Gregory-Laflamme pinch. So what we're going to have in mind here is that we're going to focus on empty spacetime in our toy model. Why empty spacetime? Well, as our string is pinching off and there's this naked singularity forming, basically everywhere around, locally, everywhere around this string, there's sort of an empty spacetime, and there's these tails that are just simply extending off to these boundary black holes. So we can imagine that if we want to extract a sort of a signal that would go in any sort of a transverse direction, it's not going to be obstructed much by these tails there, and so we can just simply forget about them and model the spacetime around as simply empty spacetime. Okay? The next thing that we're going to focus on is high-frequency modes of our solution. So these are the modes that see very short distances, but these are also the modes that can propagate very radially, sort of a kind of an S wave of propagation of our modes. And so why is this important? Well, it's important because if they can propagate very radially, then we can apply the linear approximation to extract the signal that comes from these modes. And this is actually something that has been proven to be a good approximation because it was checked in this paper by Chester and Wei that this linear results, so to say, the results that they obtained through this linear analysis exactly match the nonlinear full numerical evolution, which was sort of surprising because you would expect at least some sort of a correction, but they got actually the same results. That is to say, really, that these nonlinearities that you would encounter very close to the singularity really don't matter that much once you look at these high-frequency modes. Of course, none of these would give me a good toy model for a naked singularity if I didn't impose this last step. And this is simply to impose some sort of a scaling symmetry for my solution that would emerge from this singularity. The scaling symmetry is called self-similarity, and it's basically supported by two things. So first of all, the self-similarity is observed in the systems that undergo critical collapse. So we can see the self-similarity emerging around the singularity. But it's also supported by fluid jet systems, which are hydrodynamic analogs of these black strings. And these fluid jet systems, of course, being just hydrodynamics, we can study them much better, we understand them much better. And when the fluids simply pinch off, the pinch off also leads to a sort of a divergence in the hydrodynamic description, but this is nothing singular, so to say, nothing chaotic happening or anything. This is simply your hydrodynamic description failing, and what you have there are some molecules that are falling apart, so to say. And what people have seen in these fluid jet models is that exactly near those pinches, you get this emerging self-similar symmetry. And so we're going to assume the same type of a symmetry for our case as well. So let me just say in one slide what I mean by self-similarity. So we call this function to be a self-similar function around some point, x equals t equals 0, if it simply obeys a sort of a scaling relation. So this is the scaling relation. And depending on this parameter lambda, this function is going to be discretely self-similar or continuously self-similar, depending on whether lambda is discrete or continuous, that is, integer or real number. Now, note that this function can also be scale invariant only in just one variable, which is, of course, trivial. But it's important because it's going to make a difference once I get to the calculational part of this section. So if it's scale invariant in one variable, then we can rewrite it in terms of a log. And then we see that this scaling symmetry with respect to the log actually turns into a shift symmetry with respect to this tau. What this means in particular is that if we have our function f to be continuously self-similar, then we see that our function is going to be independent of tau. It's going to be independent of tau. Why? Well, because now I have f of tau to be equal to f of any number plus tau. And so, of course, it's independent of tau. On the other hand, if we have discrete self-similarity, then we're going to have a periodic function of a log. Periodic function of a log because lambda can here be 2 pi and so forth. So we have tau equals tau plus 2 pi. Okay. So this is the self-similar part. And now putting all of these three different things together. Yes?
Can you just take a few of this picture where the thing is pinches?
Mm-hmm.
How should where is the self-similarity there?
So we're going to get to this part.
Oh.
Okay. Well, I got to this part. So this is basically how you should think about it. So we're going to have linear gravitational perturbations that are emerging from this singularity. It's a sort of signal that you get just from popping out. It's around flat space-time. It's AdS, because we also want to extract the signal on the boundary. And this solution of linearized gravitational perturbations simply obeys the self-similar symmetry.
You construct a new solution from scratch, which is self-similar. I'm trying to understand how you motivate the self-similarity from the point of view of what's happening dynamically to start with.
Yeah, so dynamically you would expect, as the string is pinching off, you would expect that as it pinches off, there's some sort of a gravitational waves emerging from this pinch off. And so what you want to model is these gravitational waves. If you think about it in a critical collapse setting, what you model is this, so you're collapsing some sort of a scalar field, for example.
So that's not what you're doing. Like you're doing something like regular form. Like in the original regular form, I saw these beads that these guys made, right? And you can see these little beads connected by strings, and the strings get thinner and more beads form, and I could sort of see what's self-similar about it.
Yeah, yeah.
I'm trying to understand how that works here, because you have this sort of AdS scale, and things just pinch and move out to the boundary. Is there some dynamics like?
Well,
I guess I'm having trouble understanding the self-similarity of what I know about GL, which may be the wrong thing.
it's
with
not the
self-similarity
wrong
that you're
thing.
invoking here.
So is it easier to think about the critical collapse, for example? Because I feel like if one understands...
Easier, but that's not what,
No, I understand,
I
but...
don't understand why invoking that would be appropriate in this setting, yeah.
No, we're not, okay, no. We're not doing a critical collapse calculation. We're doing literally this calculation. Okay?
Why is that the right thing to do, I guess, is what I'm asking. Where do you...
So do you not expect that as the string pinches off, that you would get some sort of a gravitational waves emerging from this? It's dynamical.
That sounds plausible, but I don't understand why they have to be self-similar.
Well, this is this section over here. That this is something that you would expect your solution to have as it pinches off. It doesn't...
Why would you expect that?
Well, because this is something that we've seen here in these fluid jet models. It's also seen whenever you have the naked singularity forming, there is an emergent self-similarity around the solution, so to say. Around the singularity, sorry. So there's a universal...
Another question is that this analogy or similarity with the fluid is only a motivation to think about it.
It's only a what?
Only motivation to think about this.
Well, no. I mean, the motivation would be to think about any sort of naked singularity forming. In critical collapse, there was an explicit... people explicitly saw the emergence of the self-similarity of the solution.
Because there was no axial, it's spherical. But
yeah, that's true. I mean, that's true. There are some caveats to our assumption, of course, but we're making an assumption based on the critical collapse and these fluid jet models.
okay.
So we would just expect sort of these gravitational waves to obey this self-similarity. This could be completely wrong. I will give you that. But it's an assumption that I would say that it's least well motivated by these other examples. So that's why we impose it.
Especially deep inside the bulk.
Especially deep inside the bulk.
Right.
Yeah. Well, we're going to see. Yeah, okay. I will go through the calculations, so we'll see.
Myself. You're doing this entire setup in order to get some sort of signal that you can actually test experimentally.
If by experimentally you mean I can do a CFT calculation and see what I get, yes.
Okay. That's the part that I was trying to figure out, if it was actually something that you were going to look for.
Yes.
So, okay, so there's no way to actually know yet if that assumption can be wrong. I guess that's what I'm trying to do.
It's an assumption. It's, you know, like maybe you can think about it as, well, we did the calculation of a specific thing. The specific thing is simply gravitational waves that have some sort of a scaling symmetry, and they're simply an AdS that's empty. That calculation gives you for sure the results that we're going to get. Now, is that assumption, is that toy model correctly representing what we see when we get the naked singularity for real in the bulk? I would say it's close enough. I would say it's a first step. It's definitely something, it's the first thing that you would do, for sure. Because there's nothing else that you know about this. You only know that there's some sort of a self-similarity emerging whenever other naked singularities are formed. You have this, as I mentioned before, you have these models from hydrodynamics where this also seems to be the case. So you would assume that this is at least in the right direction. Going in the right direction. Yeah.
Because it's not really probing singularity, but suppose singularity has this property,
Yes.
kind of probing consequence of that, right? So that's
Yeah, so you're probing what kind of a, like if the singularity gives you this sort of a gravitational waves, then what we calculate is the signal of these gravitational waves on the boundary.
Probably people don't have any issue with that.
Yeah, yeah.
Probably people thinking like probing singularity.
Well, I mean, in the critical collapse setup, you are really doing that, because what these guys did for sure is do a proper numerical evolution as well as the linear analysis. And what they got, as I mentioned before, is a complete match between the two things.
Marija, do you think you can close in like 10 minutes?
I can close before. No. I can speak very fast. Okay, so what we're interested in is the simplest observable possible. It's a one-point function. So we're going to extract the stress tensor associated with these gravitational perturbations, as I just mentioned. And in order to sketch the calculation, I am not going to show you the actual calculation that we did, because that's very tedious and it's 7 pages long in an appendix. But I'm going to show you the simpler case of this critical collapse of a scalar field, the one that Chesler and Wei did. Okay? So the basic idea is, of course, that since the singularity from critical collapse comes from these self-similar fields, we make the assumption that these fields near the origin take the self-similar form, and then we simply propagate these fields up to the boundary. Okay? Okay. So we start with a linear solution for a massive scalar and AdS. That's AdS. And the solution that we obtain by solving the Klein-Gordon equation is something like this. With this factor here is added with some hindsight. That hindsight is going to be explained around here. And these omegas are proportional to n for large n. Okay, this is going to be very important. So we see simply the time-dependent part. There is some cosine coming from the AdS factors. And there is these Jacobi polynomials that explain our solution. Model our solution. Okay, so in order to construct a self-similar solution, what I mean by that is, of course, that we want to choose these coefficients, ANs, such that our phi is self-similar. And in order to do that, we focus on the behavior near the center of AdS, and we focus on these high n modes. Okay, so we go near the center of AdS. These high n modes see only like empty space-time. And so, of course, if they see empty space-time, by using a fancy Wikipedia formula, we get that those modes exactly give us the Bessel functions that you would obtain in empty space-time. So this is exactly where this n to the minus a came in, that we had to extract from these coefficients in order to make this sort of a limit. And now that we have these Bessel functions, we see that we have some sort of a form that we can use. So we have this nx, we have nx, and for large n, we have nt here, right? Because omega is proportional to t. And now we can actually see what kind of coefficients we need in order to have a self-similar form for our solution phi near the origin. In other words, we can rewrite our phi as some sort of ANs, the same ANs, that just multiply a function that's basically a function of nt and nx, right? So nx, nx, nt, this cosine doesn't matter because it's in the center. And so from here, we now see that in order to have self-similar coefficients, we simply impose that our ANs has to be obeying the self-similar scaling relation. Okay, so now we have our coefficients. Now we can go out, zoom out from our empty spacetime, center of spacetime. And we can propagate this linear field now to the boundary and read off its signal. The boundary, of course, is as x equals pi half, and we can simply read off the vacuum expectation value of the operator that is associated to this field. And through some algebra, you get that the one-point function of the CFT is basically given by this time derivative of a self-similar function around this t minus t star, where this t star is basically just the time when the signal hits the boundary. But now notice something strange. That is to say that if our singularity was discretely self-similar, that is to say our function is discretely self-similar, then this one-point function is a time derivative of a discretely self-similar function, which is to say a time derivative of a periodic function of a log. And of course, a time derivative of a log gives us 1 over the argument of the log itself. And so what we obtain is a basic behavior for this one-point function on the boundary. So we see that this one-point function actually diverges as our t approaches t star. So there's going to be some divergence in this one-point function as we approach this pinch-off. Sorry, not pinch-off. In this case, is a critical collapse. So as we form this naked singularity. So that's basically the calculation that these guys did, Jessler and Wei. We can do a similar calculation, now just with gravitational perturbations. And as I mentioned before, the formalism is mostly the same, so to say. We use Ishibashi-Kodama and so forth. We can go through these details if you want later on. But I will just show the end point of our calculation, which is to say that we can obtain, of course, the components of the stress tensor and the boundary. And what we obtain is very interesting. What we obtain basically are these three things. That is to say that the energy density and the pressures vanish as we approach the boundary. The momentum components remain constant, but the shear actually diverges. So this is our... So this is basically... Sorry?
Approaching the boundary means that t goes to pi over 2, right?
Yes. Yes.
So it involves something is approaching the boundary and it's going to hit it pi over 2.
Yeah, you can imagine these gravitational waves just propagating out. Or from a CFT point of view, you're evolving towards a naked singularity from some tentative CFT calculation. So we see that the boundary signal is not smooth, basically oscillates an infinite number of times before the singularity occurs, and therefore reaches arbitrarily high frequencies.
And this, so the shear here I is not equal to j?
No.
So
That would be momentum.
Components are like the TT components?
Sorry, yes, that would be, sorry, the pressure, yes. Okay. So there are some obvious questions that we can ask now. I'm going to ask them quickly because who is going to kick me out? So first question that one can ask is, how does the CFT actually resolve the singularity? That's the most obvious question that one can ask. And I don't have a proper answer, so to say, but we can give a hint. So what we can expect. So what our analysis suggests is that we should obtain only a few high-frequency quanta on the boundary, right? So our energy density vanishes, but we have highly energetic particles, and they're having these large shears. And one analogy that one can think of is, for example, gamma rays. So gamma rays are very highly energetic, and they pass through us every day, so to say, from the skies and so forth. But of course, if we only have a few of them, they're not very deadly. And so one can think of these gravitational waves that we obtain on the boundary as also not being very deadly for the CFT in some particular sense. Related to this question is, of course, well, we obtained that the stress tensor diverges. Doesn't matter that it's a shear diverging, it's still a divergence. So one can ask if we can actually evolve on the CFT side beyond this point t star, beyond, so to say, pi half. And I would say that at infinite n, which is the case that we are in, it seems to be the case that we cannot actually evolve further. But of course, this should not deter you from actually doing physics with these things, because you only need small finite n corrections in order to allow the evolution beyond this critical time. So we have 1 over t minus t star. This is basically proportional to n squared. So if you make n finite, you don't have any problem on the CFT side. And of course, there's the most natural question, or, well, can we predict the singular structure of the stress tensor purely from the boundary theory? So can we do some sort of a CFT calculation that corresponds to a creation of a naked singularity and see that we get the same type of a stress tensor structure? So this is basically saying that our results give us a prediction for how this web should behave. And this tentative boundary theory, which could be some sort of a matrix model on n equals 4 or any other CFT, well, we need to then see how the system would evolve past the moment when the certain matrix operators acquire these large values that scale as n, right? So we want to go beyond the infinite n limit. We want to be in the finite n regime. So those are all the questions that I could think of for now. So let me just summarize. We saw that examining this gravitational Flam instability in AdS spacetimes has led us to a variety of new results, new phases that black objects can exist in. And we also see that if we do this calculation in AdS, then we are also allowed to look at the boundary point of view of what's going on when we try to create this naked singularity. So the takeaway lessons, so to say, is that the evolution of these black strings lead to new types of dynamics that are not seen in the flat case. For example, these black tsunamis would not be there. But also, we can extract that the cosmic censorship can surely and indeed be violated in AdS. It's just that this violation is in a very particular sense small, but we can also see through this toy model how small it is on the boundary. And now there is some future work. I'm just going to flash here. This future work basically tells us, well, now you were working with these fixed boundary geometries with these black holes. Why don't you put some brains inside instead? So instead of having a boundary, fixed boundary geometry, we just put some brain inside, some sort of a Kurt-Randall brain, and we put black holes on top of these brains. And we can try to play the same games. We can try to evolve with the large D equations. And the one thing that I'm hoping to see, but we are now in the progress of it, is that maybe we can kick this black hole hard enough on the brain so that this black hole basically starts evaporating on the boundary, on the brain, sorry. And the analog of that would be, of course, filling up in the higher dimensional bulk, making this large AdS analog. And as the black hole would be evaporating on the brain, this black hole would be getting bigger, but there would be, of course, at the end point of evaporation, there will be some sort of a pinch-off, and then the goal would be to match this pinch-off that was from the higher dimensional bulk of Gregory-Laflamme pinch-off to the end point of evaporation black hole. Sorry, was that understandable? The naked singularity that one gets from the end point of evaporation, you want to match to the Gregory-Laflamme pinch-off naked singularity. That's basically what I wanted to say. And that's what I want to see. Of course, we haven't gotten there yet. And that would be interesting because then that would allow us to actually reduce this category of naked singularities to just one big set. One big set that all of them have self-similarity, that all of them can have the same type of a signal and so forth. And of course, there's always the faraway future work, which includes actually doing the proper CFT calculation and see how this naked singularity forms, but that's very, very far away. And so I thank you, and I leave you with a real-life example of a black tsunami. Of course, you cannot see anything here, but those are birds in Greece forming a black tsunami. Okay, thank you.
Maybe you can have one quick question for Marija. Also, let me remind you all that Marija is here until next Thursday, so we have a lot of time to talk.
So you can ask me any other time. Yeah, that's also true.
Thank you, Marija.